In this part, we'll look at what makes up a typical motor branch circuit. A motor branch circuit, or motor branch, is a circuit that provides power and protection for a motor. According to the National Electrical Code, a motor branch must have a means to disconnect the entire branch from its power supply, and a means to protect the branch components from the potentially damaging effects of excessive current. We can use a couple of simplified schematic diagrams to identify the different parts of a typical motor branch. This is a schematic of a motor branch that uses a circuit breaker as its disconnect device. The motor branch extends from the line or power source side of the circuit breaker to a three-phase motor. The power source is not shown to help keep the illustration clear. To the left of the motor branch is a section labeled feeder. The feeder is the circuit that supplies power to the motor branch. In this example, the feeder has a feeder breaker that can complete or interrupt three separate motor branches. We can better see what's involved in a motor branch by focusing our attention on a single motor branch circuit. To the right of the feeder section is a circuit breaker that can open the motor branch and isolate it from the power supply under either normal or abnormal conditions. This is an example of a circuit breaker. Under normal operating conditions, it can serve as a disconnect device. For example, when the breaker handle is in the on position, contacts inside the breaker are in the closed position, completing a path for current to flow from the feeder to the motor. And when the handle is moved to the off position, the contacts inside the breaker open to disconnect the motor from its power supply. Under abnormal operating conditions, the breaker's contacts open automatically to protect the motor branch from excessive current. To the right of the circuit breaker is a controller section, which is a motor controller. A motor controller is a device or group of devices that control and protect the operation of a motor. For example, a magnetic motor controller uses electromagnetic switches to perform control functions. In addition, the controller contains overload devices that operate to protect motors from damage that could result from overloads. Some magnetic motor controllers also provide low voltage protection. Insufficient voltage can result in motor damage. When the voltage a motor receives decreases, current increases, and the increased current could damage the motor and its windings. The last device represented on the diagram is the motor served by this motor branch. Now, another common type of motor branch uses a safety switch instead of a circuit breaker as a disconnect device. A safety switch can also open the motor branch and isolate it from the power supply under either normal or abnormal conditions. In all other ways, this motor branch is the same as the one with the circuit breaker we just saw. A safety switch is usually a knife-type switch that is manually operated by means of a handle and linkage. This particular safety switch has fuses installed in it to protect the motor branch from short circuits. Now that we've looked at a typical motor branch, let's focus our attention on the components that protect it. Typically, these components protect a motor branch from high levels of current, which you may hear called an overcurrent condition. Two types of overcurrent conditions that can occur in a motor branch are short circuits and overloads. An overcurrent caused by a short circuit is usually extremely high, so the circuit's protective devices must act quickly to prevent damage. An overcurrent caused by an overload is generally not as high, and the protective devices do not act as quickly. Most overcurrent protective devices have inverse time characteristics. For overcurrent protective devices, inverse time characteristics means that the higher the overcurrent, the quicker the protective device will operate. Two types of devices that are used to protect a motor branch from the high current associated with a short circuit are circuit breakers and fuses. Both circuit breakers and fuses open the circuit when excessive current flow is detected. Circuit breakers are designed to compensate for momentary excessive surges of current. They can be reset and used again after they've operated to open a circuit. A fuse is a device containing an element that melts when current flow through it rises above a designated value. When the element melts, the path for current flow through the fuse and therefore through the circuit is interrupted. This condition is commonly referred to as a blown fuse. Many fuses cannot be reused after they have interrupted current flow and must be replaced. There are also fuses in which the element that melts is part of an internal component that can be replaced. Once the internal component has been replaced, the fuse can be reused. Now, overload protection in motor branch circuits is typically provided by overload devices. Overload devices are usually part of a motor controller. When an overload occurs, an overload device opens a set of contacts to interrupt current flow. There are two basic types of overload devices: thermal overload devices and magnetic overload devices. Thermal overload devices generate heat that activates the device when an overload condition occurs. Magnetic overload devices generate a magnetic field that activates the device when an overload condition occurs. Take a moment now to check your understanding of motor branch circuits and their components. In this part, we'll look at safety switches and at fuses that are commonly used in safety switches. Safety switches are often used as disconnect devices in motor branch circuits. A safety switch is usually a knife-type switch that is manually operated by means of a handle and linkage. Many safety switches are interlocked to prevent the doors of their enclosures from being opened unintentionally. For example, this safety switch has two interlocks that can be overridden with a screwdriver. The bottom interlock can be used to open the safety switch's door when the switch is in the off or open position. When the interlock is turned with the screwdriver, the interlock is overridden and the door can be opened. The top interlock must also be turned to open the safety switch when the switch is closed or in the on position. For example, you may need to open a safety switch's door to take voltage readings while the switch is in the on or closed position. Before you override any interlock, you need to check your facility's policies and procedures and make sure you follow all applicable safety procedures. After all necessary tests have been completed, this safety switch's interlocks are reset by closing the enclosure door firmly. Now, most safety switches used in motor branch circuits have fuses installed in them. The purpose of the fuses is to protect the circuit from being damaged by the high current that results from short circuits. A common type of fuse used in motor branch circuits is a cartridge fuse. We can see all of the parts of a typical cartridge fuse in this illustration. This fuse consists of a casing, two contact points, and a fuse element, which is commonly called the fuse link. The casing protects the fuse link from being broken or damaged and allows for handling the fuse. Casings are usually made of paper or glass fiber. The contact points are the surfaces or projections that connect the fuse link with a fuse holder. The fuse link is an alloy wire or strip that melts when its current limit is exceeded. There are two basic types of contact points: knife type or projecting end contact points, and ferrule or round end contact points. Contact points are made of a conductive material such as brass or copper, and they may be silver-plated to improve the conductivity of the contact surface. Fuses come in a variety of sizes and shapes, depending on the voltage rating and the application. Usually, the physical size of a fuse can help you identify its voltage rating. Two general types of cartridge fuses that are commonly used in motor branch circuits are one-time cartridge fuses and renewable link cartridge fuses. A one-time fuse, as its name suggests, is a fuse that must be discarded after it blows. A renewable link fuse contains a link that can be replaced with a new one so that the fuse can be used again. To replace a blown fuse link in a renewable link fuse, you first unscrew the end of the link fuse, then take out the blown fuse link. Next, put in a replacement link that is the same type as the blown fuse link. Most renewable link cartridge fuses will accept links of different current ratings. You should make sure that you're using the proper replacement link by checking the current and voltage ratings stamped on the replacement links. Whenever you replace a fuse link, make sure that the fuse casing is labeled to identify the ratings of the new fuse link. This way, if the ratings marks on the link are destroyed when the fuse blows, the label on the casing will identify the proper ratings for the replacement link. After the new link is installed, screw the end of the fuse back on. A type of cartridge fuse that is specifically designed for motor branch circuit protection is a dual element fuse. A dual element fuse has two types of elements: short circuit and time delay. For example, this dual element fuse contains one fuse link that has two short circuit elements, one at each end of the fuse link, and a time delay element located in the middle of the fuse link. The short circuit elements work like one-time fuses. They melt when their current limit is exceeded. The time delay element is made of a special alloy that is designed to allow some momentary overload to occur. However, if a small overload continues for an extended period of time, or if the magnitude of the overload increases to a sufficiently high level, the alloy melts all at once, opening the circuit. The last type of fuse we'll look at is called a current-limiting fuse. A current-limiting fuse is a special type of one-time fuse that's designed to blow more quickly than a typical one-time fuse. For example, a one-time fuse with a current rating of 30 amps may allow 32 to 33 amps to flow through it for a short time before it blows. A current-limiting fuse with a current rating of 30 amps will blow more rapidly if the current exceeds 30 amps and will not allow a higher current to pass. In general, fuses are classified as being either current-limiting fuses or non-current-limiting fuses. Letters are used to identify specific types of fuses within these two general classifications. After the reason why a fuse has blown has been investigated and corrected, it's important to replace it with a fuse of the correct rating and type. To make sure you have the right fuse, you can check the size of the fuse, any labels that are on the fuse, and the ratings that are stamped into the fuse's metal contact ends. You may also find the fuse's current rating stamped on the fuse holder or provided on electrical diagrams for the circuit. But let's say that none of this information is available and that you need to replace a blown fuse. What should you do? Well, there's a rule of thumb that you can use as a temporary measure to identify the appropriate fuse. First, check the nameplate on the motor branch's motor to find out what the motor's running current is. In this case, it's 92 amps. Next, multiply the running current by 150%. In this example, 92 multiplied by 150%, or 1.5, is 138. So you should look for a fuse that is rated to handle 138 amps. If the exact rating is not manufactured, go to the next highest rating that is made. In this example, a 150 amp fuse is used. It's important to remember that using the rule of thumb technique is only a temporary measure. The fuse rating should be checked out as soon as possible in the manufacturer's instructions or the plant's electrical diagrams. Then a permanent replacement fuse of the proper rating should be installed. In this part, we'll look in some detail at typical molded case circuit breakers that are used in motor branch circuits. A circuit breaker is a device that is used to interrupt current flow in a circuit under normal or abnormal circumstances. A molded case circuit breaker is a circuit breaker that is fully enclosed in an insulated housing. In motor branch circuits, circuit breakers typically perform two functions. They interrupt the circuit to protect it from damaging effects of overcurrent, and they serve as disconnect devices. The highest current at rated voltage that a breaker is designed to interrupt is referred to as the circuit breaker's interrupting capacity. The interrupting capacity of a molded case circuit breaker is usually marked on the breaker's casing. Now, the current value at rated voltage at which a circuit breaker interrupts current flow, or trips, is called its trip point. Many circuit breakers are designed to carry a specific amount of current without tripping. There are also some circuit breakers whose trip points can be adjusted. The selection or setting of a breaker's trip point is based on the amount of current that the branch circuit is designed to carry. Most circuit breakers that have adjustable trip points have the current values for each setting marked on the breaker case. A circuit breaker works like this. When excessive current flows through the breaker opens or trips automatically to interrupt the flow of current. This circuit breaker can be reset by moving the breaker handle first to the off or reset position and then to the on position. This procedure resets the circuit breaker and allows the circuit to be re-energized. The casing of a molded case circuit breaker has three primary functions: to house the breaker's components, to protect the functional components from contamination and damage, and to prevent personnel from touching energized components in the breaker. Molded case circuit breakers require relatively little in the way of maintenance. Essentially, the only maintenance that is required is to make sure that the conductor connections are tight and free of corrosion, and that the breaker is kept dry and free of accumulated dust and dirt. If problems do occur in a molded case circuit breaker that is rated at 100 amps or below, the entire circuit breaker is usually replaced. For circuit breakers that are rated above 100 amps, the general procedure is to replace any defective parts. As we mentioned earlier, molded case circuit breakers automatically trip to provide overcurrent protection for motor branch circuits. The most common methods that are used to provide this automatic trip feature are thermal, magnetic, and a combination of the two. All three methods have an inverse time characteristic. That is, the higher the overcurrent condition, the faster the circuit breaker will trip. Thermal circuit breakers operate in response to changes in temperature. Most of these types of circuit breakers have a bimetallic strip inside of them. This is a simplified illustration of a bimetallic unit from a thermal circuit breaker. It consists of a heater element which carries the branch circuit's line current, a bimetallic strip which consists of two different metals that are bonded together, and a spring-loaded mechanical linkage, and a set of contacts. The contacts are in a control circuit. When the contacts open, the control circuit trips the circuit breaker. The two metals in the bimetallic strip expand at different rates when the strip is heated, causing the strip to bend. Under normal circumstances, the bimetallic strip holds the mechanical linkage in place, keeping the contacts closed. The control circuit current passes through the closed contacts. The heater element heats the bimetallic strip in proportion to the line current. If the line current becomes excessive, the heater element heats the bimetallic strip enough for it to bend and release the mechanical linkage. When the mechanical linkage is released, the force of the spring pulls the contacts open. This interrupts current flow through the control circuit, which trips the circuit breaker. As the strip cools, the metals contract and the strip straightens, so that it once again holds the linkage in place. The linkage then holds the contacts closed, which makes it possible to reset the circuit breaker. Magnetic molded case circuit breakers use the magnetic field produced by current flow to operate. In these circuit breakers, the trip element is a magnetic trip device. We'll use this simplified illustration to see how a magnetic trip device works. The device consists of a coil of wire wrapped around an iron core and a set of contacts that are held together by a spring. The coil carries the line current. The contacts are in a control circuit that operates to trip the circuit breaker when the contacts open. When current flows through the coil, it creates a magnetic field. The strength of the field increases as the current increases. When the current reaches a predetermined value, the magnetic field increases enough to overcome the force of the spring and pull the contacts apart. The open contacts interrupt current flow in the control circuit, which operates to trip the circuit breaker. When the circuit breaker trips, current no longer flows through the coil. The magnetic field collapses, and the force of the spring closes the contacts, which makes it possible to reset the circuit breaker. The last type of circuit breaker we'll discuss is a thermomagnetic molded case circuit breaker. This type of circuit breaker contains both a bimetallic strip device and a magnetic coil device. The bimetallic strip provides a time delay to allow for momentary overcurrents, such as surges that occur when a motor starts. The magnetic coil provides an immediate trip on high overcurrents that can result from short circuits. In this part, we'll look at how you can maintain a motor branch circuit to help prevent trouble from occurring. We'll start with installed grounds. It's important to maintain installed grounds to ensure the safety of personnel and equipment. An installed ground is an intentional electrical connection to earth or ground. Two types of grounding systems are hardwired or low-impedance grounding systems and high-impedance grounding systems. A major difference between the two systems is that a high-impedance system contains a device, such as a resistor or a transformer, to limit current flow, while a low-impedance system does not. We'll focus our attention on low-impedance systems because low-impedance grounding systems are generally used with motor branch circuits. Now, just as there are two types of ground systems, there are also two types of grounds you should be aware of: system grounds and equipment grounds. In a system ground, a point in the current-carrying circuit is intentionally connected to ground. In an equipment ground, one of the pieces of equipment in the circuit, such as a motor frame or a safety switch's metal enclosure, is grounded. For example, this is a simplified diagram of a hardwired or low-impedance grounding system. A low-impedance ground is an intentional low-resistance path for current flow to ground. The diagram shows a motor branch circuit with a circuit breaker and a motor with an equipment ground, and a secondary Y transformer that feeds the motor branch circuit. The transformer has a low-impedance ground connected at its center. If an accidental ground occurs in the motor, current will flow through the installed ground, through ground or earth, to the grounded point on the transformer. This overcurrent will operate the breaker's overcurrent device and trip the circuit breaker. To maintain installed grounds, you need to check both equipment grounds and system grounds. Make sure that the ground cables are in good condition and that the connection points are of the proper size and that they're mechanically strong, clean, and in good condition. Now that we've looked at installed grounds used with motor branch circuits, let's take a general look at how preventive maintenance can be performed for motor branch circuits. In our example, a circuit breaker is used as a disconnect device. The circuit breaker is enclosed in the same housing as the branch circuit's motor controller. Preventive maintenance is routine periodic maintenance that is performed to keep equipment in good working, trouble-free condition. Preventive maintenance can be invaluable in locating potential problems before they become actual problems. Before any work is done on a motor branch circuit, the circuit must be de-energized, locked, and tagged out according to company procedures. Next, the door to the housing is opened. Then a voltage tester is used to make sure that the circuit is de-energized. First, the electrician needs to make sure that the voltage tester is working properly. Since there is power on the line side of the breaker, the line voltage can be used as a known source. The voltage tester indicates that voltage is present on the line side, which means that the tester is working properly. In this example, the voltage tester indicates 0 volts on all phase-to-phase and phase-to-ground tests, which means that the breaker is de-energized. Finally, the voltage tester is used to test the incoming power line again to make sure that the tester is still working properly. In this example, the next circuit component to be checked is the motor controller. First, a voltage tester is used to make sure the controller is de-energized. The controller is de-energized, so the interior of the controller's housing can be inspected for dirty or loose connections. If the controller is dirty, it should be cleaned with a small brush. Dust and dirt can cause binding of moving parts as well as grounds. Any loose connections can be tightened with a screwdriver. Next, the entire controller should be checked carefully for other signs of problems, such as burnt insulation and loose parts. If there are no problems, the controller's contactor can be removed, checked, and cleaned. The contactor can then be replaced, and the controller's door can be closed. The last component to be checked in this motor branch circuit is the motor. First, the motor's ground wire should be checked to make sure that it's secure. Then, a visual inspection of the motor should be made for loose or damaged parts. The motor's opening should be checked to make sure that there is no unusual accumulation of dust or any obstructions. The openings provide the motor with a means of ventilation for cooling, so they must be kept clear. If visible, the motor's insulation should be checked to make sure that there are no burnt areas. The bearing housing should be checked to make sure that there is no leaking grease or oil, and the entire motor should be checked for signs of dampness. A complete check of a motor includes inspecting it while it is running. To do this, the motor branch circuit must be put back into service. After the motor has been running for a few minutes, it can be checked to make sure that it is operating properly. For example, a motor that is operating correctly should have a smooth, steady sound. By carefully listening to an operating motor, you may be able to detect an unsteady sound or an increase in motor noise that could be an indication of a problem, such as an electrical fault or bearing failure. Unusual movement of the shaft or vibration of the motor can also be an indication of a problem. Vibration can be felt as well as heard, so it's a good idea to feel the motor carefully to locate the area of the greatest vibration. You must use extreme caution when you do this. For instance, if there's a problem with a bearing, the bearing housing may be hot enough to burn you. Some motors have instruments installed in them to measure temperature and vibration. For other motors, you may need to use a contact pyrometer to measure temperature and a vibration meter to measure vibration. Regardless of the instruments that are used, the readings you take should be compared to previous readings taken under the same conditions to see if a trend is developing. A trend toward increasing temperature or vibration, or both, may be a sign of a problem that will cause a motor failure in the future. A trend of increasing reading should be reported to a supervisor. In this part, we'll look at how you can troubleshoot a motor branch circuit to locate the cause of a problem. This is a simplified diagram of the motor branch circuit we'll use as an example. The diagram shows one feeder with a feeder breaker supplying 3 branch circuits. For simplicity, the diagram illustrates the components of only one of the motor branch circuits. The circuit contains a circuit breaker, a motor controller, and a motor. We'll say that the motor in this motor branch circuit has stopped running, and that the motors in the 2 other motor branch circuits supplied by the same feeder are running normally. The overloads for the non-operating motor have checked out okay, and the motor cannot be restarted. Since the other 2 motors are operating normally, the problem is isolated in one motor branch circuit, which also means that the feeder can be eliminated from consideration. An effective way to troubleshoot the motor branch circuit is to start at the electrical middle. This method of dividing a circuit allows about half of the circuit to be eliminated on the first test. In this example, the motor controller is approximately at the electrical middle, so it is a good starting point. The housing of this motor controller also contains the circuit breaker. This arrangement makes troubleshooting more convenient since both parts are located together and are easily accessible. To begin troubleshooting, the motor controller should be checked for voltage while it is energized. This controller has a safety feature that prevents its door from being opened while the controller is energized. To get around the safety feature, the circuit breaker is switched to the off position, the controller's door is opened, and the breaker is switched back on again to energize the controller. Once the door is open, a voltage tester or a multimeter set for voltage readings can be used to make sure that there is incoming power. The voltage tests are made at the controller's 3 line leads. The line leads carry power from the feeder through the circuit breaker to the motor controller. If power is available at the line leads, it is logical to assume that the problem is in the half of the circuit between the motor controller's line leads and the motor. If there is no power available at the line leads, then it is logical to assume that the problem is in the half of the circuit between the line leads and the feeder breaker. If there is power available at the line side of the circuit breaker, then the wiring from the feeder breaker to the circuit breaker is in working condition. If there is no power, then the problem is in this wiring. In this case, the wiring would have to be inspected, tested, and, if necessary, replaced. If a visual check shows that the circuit breaker has tripped, the reason for the trip must be determined and corrected. Then the breaker can be reset and closed again so that voltage tests can be made. In this example, power is available at the circuit breaker's line leads, so the next check is for voltage on the output side of the circuit breaker. If there is voltage at the output side of the circuit breaker and power is available on all 3 phases, then the circuit breaker is in working condition. If there is no indication of voltage at the breaker's output side, then the circuit breaker must be examined further. Now, if the half of the motor branch circuit between the feeder and the motor controller is checked and found to be functioning properly, the other half of the circuit from the motor controller should be checked. To check out this half of the motor branch circuit, you should first check for voltage on the terminals for the motor leads going from the controller to the motor. If the test device indicates voltage at the motor lead terminals, the controller is operating properly. If no voltage is indicated, the controller will have to be checked further. For example, the controller's contactor and overload devices can be checked to make sure that they're operating correctly. If the controller is operating correctly but the motor will not run, then the motor leads from the controller to the motor and the motor itself will need to be checked. If the motor leads check out, the motor should be de-energized at the motor controller and the controller should be locked and tagged according to company procedures.